the problem of the origin of the universe, in a sense. Is it possible to talk intelligently about the beginning, or will we forever be condemned to a kind of Zeno-like frustration in which our theories approach ever more closely to the beginning? They're quite close now. There are theories that address the evolution of the universe back to a tiny fraction of a second, 10 to the minus 42nd of a second.
Keep watching to learn more. You can now download all 9 copies of the New Thinking Aloud magazine for free, or order beautiful printed copies. Go to newthinkingaloud.org. New Thinking Aloud is presented by the California Institute for Human Science, a fully accredited university offering distant learning graduate degrees that focus on mind, body, and spirit. The topics that we cover here. We are particularly excited to announce new degrees emphasizing parapsychology and the paranormal. Visit their website at cihs.edu.
Book 4 in the New Thinking Aloud dialogue series is Charles T. Tart, 70 Years of Exploring Consciousness and Parapsychology, now available on Amazon.
Thinking Aloud. Conversations on the leading edge of knowledge and discovery with psychologist Jeffrey Mishlove.
Hello and welcome. I'm Jeffrey Mishlove. Our topic today is Understanding the Universe. With me is one of America's premier science writers, Professor Timothy Ferris, author of The Whole Shebang, as well as many other books, including Coming of Age in the Milky Way and The Mind Sky. Timothy is a professor emeritus at the University of California, Berkeley, where he has taught astronomy, English, and journalism. Welcome, Timothy.
Glad to be here.
It's a pleasure to be with you. The whole universe is probably just about the largest subject anybody can deal with, can grasp. In fact, it's difficult for people to grasp. I suppose when we think about it, the very first organizing principle is the notion of the Big Bang.
The Big Bang theory is a big theory. It's not just a narrow, rigid construction that's likely to fall apart tomorrow. I think of it as more like Darwin's theory of evolution, in that it is an arena within which a number of other theories can and do compete and thrive. I think the cosmology in the 21st century will be conducted within the arena of the Big Bang theory, but at the same time, as has happened with Darwin, the theory itself will evolve and change, not beyond recognition, but certainly be a lot different than the basic ideas of the Big Bang theory that date back now almost half a century.
Mm-hmm. The fundamental idea is that the physical universe, as we can observe it, began in some sort of an explosion of space and time itself.
The Big Bang theory was predicted inadvertently by Einstein's general theory of relativity, which showed that cosmic space can be curved, indeed can't avoid being curved by the gravitational attraction of the matter in the universe, so that we can map space as if it were, for instance, the surface of a balloon. And if you imagine that balloon having begun at infinitesimal size and inflating ever since, all of the three-dimensional universe we inhabit is represented as the surface of that balloon. Predicted in general relativity and then discovered in the sky by astronomers who knew nothing of the prediction. It's one of the great confluences of theory and observation in the whole history of science.
Mm-hmm. And the particular observations, I think, are that galaxies are receding in every direction from the Earth.
Astronomers started to measure the spectra of galaxies, looking for velocities in them for reasons that were quite unrelated to cosmology. And we're astonished to discover that most galaxies, the ones outside our immediate neighborhood, where the galaxies are bound together gravitationally, were moving apart, and that the further you looked, the faster they were moving. And that's the signature of expansion. And there came a great moment when Edwin Hubble, who discovered the expansion in the sky, was visited at the Mount Wilson Observatory in California by Einstein, whose theory had predicted it. And the theorist and the observer together realized that between them they had discovered really the fundamental fact of cosmology that to me represents, for any species in the universe, the dividing line between, let's say, adolescence and adulthood, the point at which you have learned, the fundamental fact about the history of the universe, with which you are then enabled to begin seriously to study the whole picture.
So the basic idea is, if it's expanding in every direction around us, that if you were to run the movie backwards through time, at some point it was a point.
Yes, and there are ways that you can test this. And one way is that you say, well, there's a certain amount of energy in the whole universe, and if you put that energy in ever smaller volumes of space as you move back in time, the temperature of the universe should go up. It's just the way that if you pump air into a bicycle tire, it heats up because the air is being compressed. Now, if that were the case, then you can do the physics. It's actually very straightforward, and determine that in the early days, the universe should have been as hot as the surface of a star. And everyone in the universe should be able to look back in time, because as you look further in space, it takes longer for the time to have traveled through space, and see back behind it all a kind of a sheet of glowing radiation left over from that early fireball. And that has been found. It's the cosmic microwave background. It conforms exactly to the spectrum predicted by theory, and it contains within it signs of the incipient formation of structure that led later on to the existence of galaxies, clusters, stars, and planets.
So basically, when it comes to the Big Bang, we've got, on the one hand, the data of the galaxies moving away from the Earth in every direction, faster and faster the farther away they are. We have Einstein's theory of relativity, which predicts that this should happen, and we have the background microwave radiation, which is sort of the remnants of the original explosion, or at least a phase shortly after the original explosion.
That's right, and the phase known as photon decoupling, technically it's the time when the primordial matter thinned out enough to release the light so that the photons weren't just bumping into particles of matter all the time. And there are a couple of other points, too, that support this conception. One is chronology. If the universe has a finite age since the beginning of expansion, then one ought not to find anything in the universe older than that time. And while there's still some doubt as to the exact value of that age and a certain amount of error, it seems to be the case that the oldest stars date back to the early universe, but not earlier. You don't find things around that are older than the universe as a whole. And another important piece of data consists of the fact that the chemistry of the initial fireball should have built a certain quantity of the light elements, particularly helium, so that if you do the physics, you find that about a quarter of the material in the universe should have been converted into helium in the Big Bang. And the cosmic abundance of helium is indeed around 25%. So all in all, I'd say there are maybe 5 major avenues of research that all support this strange conception that the universe hasn't been here forever, at least not in its present form, but really did have an origin back roughly 15 billion years ago.
And there's enormous scientific consensus about all of that, but I think the really interesting aspect of the Big Bang Theory are some of the philosophical questions that emerge from it. For example, we have to begin to think about time a little differently. I think our conventional view of time is that at any given moment in time, there was always a moment before that. The same thing with space. In any given position in space, there ought to be another position beyond it. But the Big Bang seems to suggest that there was a moment before which there was no time.
And this is the problem of the origin of the universe, in a sense.
Yeah.
Is it possible to talk intelligently about the beginning, or will we forever be condemned to a kind of Zeno-like frustration in which our theories approach ever more closely to the beginning? They're quite close now. There are theories that address the evolution of the universe back to a tiny fraction of a second, 10 to the minus 42nd of a second. That's a zero, a decimal point, and 41 more zeros. That's a very tiny fraction of a second, and there's hope of being able to push that back even further. But when you get very close to the beginning, quantum physics comes into play. You have to start to envision the fabric of Einsteinian space-time having been broken up into a kind of foam. And one of the characteristics of that foam, if you're shattering space-time into pieces, is that the arrow of time, which in our modern classical universe is very dependable, you wake up in the morning and it's the next day, it's not the previous day, that arrow is also shattered. So the direction of time itself gets lost in a kind of quantum flux near the beginning. And this may be a very important insight in trying to understand what is meant by the origin, and in dealing with this old paradox of how can you talk about something having occurred before which nothing occurred.
Well, time seems to me, in reading your book, The Whole Shebang, to be the biggest mystery about the universe. As I understand it, the conventional view today, the accepted view, the standard view is that the universe is roughly 15 billion years old. Before that, there really was no time at all to speak of. And yet, according to Einstein's theories, a photon traveling across the universe would experience no time.
Which that's a very interesting point, isn't it? That time, there is in here somewhere, there is something of great value. No one quite knows what to make of it yet. But you're quite right that for a photon traveling at the velocity of time, time does not exist. All times and spaces are the same to the photon.
Yeah.
What that means scientifically, no one has yet been able to intuit. But one would hope that in the next century, something can come be viewed through that keyhole. You know, that would illuminate this old mystery of time about which shelves of books have been written, and no answer has been found.
So there is a sense, and you write about it, in which we can view the universe in two ways. One is a universe that exists in time, that began when time began, and which is constrained by time. That is, when we look into the far reaches of the universe, we're looking into the past, because it takes, from our perspective, it takes a photon that's 15 billion light years away. It takes it 15 billion years to get to us, although from the perspective of the photon itself, it took no time at all.
Yeah, it's an amazing situation, but of course from our perspective, looking outward, it means that the whole tapestry of cosmic history is laid out for observation. This is the sort of thing that the Hubble Space Telescope has been so successful at doing. To look deeper into space and to actually see how the universe was when it was substantially younger than it is today. This is a great advantage in cosmology. You know, a historian of human affairs has to rely upon reconstruction from a few books, excavations at archaeological sites and so forth, and piece together the rest. But in cosmology, it's as if a historian had a telescope through which you could peer and see Socrates at the marketplace in Athens. It really is possible to look out and back in time, see galaxies as they have moved through various stages of their evolution, and piece together the story not just through inference, but through direct observation.
Well, that's one of the great miracles of cosmology today. I suppose in recent generations, it's moved from being a study which was mostly speculation and a lot of myth to one which is really being well integrated into the sciences.
Yeah, one of the myths about cosmology is that it is still a myth, and that's just not the case. Sometimes people say to me, well, you know, the explanations that you accept for the universe are just another story like the ones that were told around campfires thousands of years ago, and someday they'll be supplanted by others. I think, unfortunately, many students find an excuse for not inquiring into science on the mistaken belief that these theories all get overthrown anyhow, and so I don't need to study them. You can ask a question which is posed by Steven Weinberg, the American physicist, Nobel laureate, Very interesting question. In the 20th century, how many major well-established theories of physics have been overthrown? The answer is zero. Science is not just a matter of telling stories. It's an improved method of inquiring about nature. And it has been possible to move cosmology from the status of myth to the loftier status, in my view, of something approaching fact.
Well, it's interesting because one can't help but read your books and come away with an extraordinary sense of awe for the enormous amount of human resources in terms of time and brain power and dollars over many, many decades that have gone into solving these difficult problems. And the answers are truly, they're mind-boggling. We're talking about thinking about the beginning of time. We're talking about thinking about time stopping for a photon. And if we look at space itself, we have to think of space in new ways from the perspective of cosmology. For example, you've written quite a bit about black holes and the problem of gravity. And while we here on Earth experience gravity as a force on our bodies, and I think we think of gravity as a force, you point out that it's equally valid to consider gravity as curvature in space.
Yeah, that's the formulation in general relativity, is that gravity is just our experience of the local curvature of space, which in this case sitting here is caused by the concentration of mass in the Earth. In the Big Bang theory, you are confronted with what is in general relativity a paradox, that is an infinite curvature of space at the beginning. And this, you could imagine a situation in which this could only be studied in terms of this remote event, the Big Bang. But fortunately, nature seems to have provided models much more recently and closer to us in space and time in the form of black holes. A black hole is an infinite curvature of space, and they seem to be all over the place. They're at the centers of galaxies, including our own galaxy. So it's going to be possible to actually study these things and directly observe them. These observations are already going on. And to learn something about what happens when space is infinitely curved. It's very important in physics because when you go over that waterfall, the event horizon of a black hole, you reach the point at which relativity breaks down. Something new is needed, and putting together that new and hopefully more overarching theory is one of the main tasks confronting the physics of the future.
Mm-hmm. Well, it's interesting to think that when we go into a black hole, or when we go back to the beginning of the Big Bang, we reach a point at which the laws of physics as they are generally understood can break down completely.
Yeah, the job of physics is not done. I was amused to see that there continue to be books and articles talking about how science is all finished, and we won't need to have scientists anymore, that we have all the answers. That's not the way I read it. It seems to me as if enormous prospects lie ahead for the future. Just in quantum physics, there are developments that suggest that everything we've seen in the 20th century in physics, which has been enormous progress, is as if we had as a sun a binary star system, and one sun had risen, and now behind it there is going to come this much larger sun, and to cast everything in a much different light. The future of quantum physics alone promises to be such as to render all of the 20th century merely preface. So I don't think this enterprise is anywhere near being over. I think we're much closer to the beginning than we are even to the middle.
Mm-hmm. And I gather one of the great challenges for cosmology today is to unify, if possible, the two major theories that we have, the theory of relativity, which is a classical large-scale theory of the universe, and quantum theory, which deals with the subatomic structure.
Yeah, relativity is a complete theory for what it covers. And where it breaks down very elegantly. All the numbers go to infinity. Einstein tips his hat, leaves the stage. The theory has done its work. You're now in some new realm. You need a new guidebook. Quantum physics is very successful. It successfully predicts the outcome of every fundamental interaction in the known universe. But it has an aesthetic flaw in that to work quantum mechanics equations, you have to plug in a lot of quantities, which are only known from experimental results. There's a little thing called the particle properties data book that you can carry in a coat pocket. And when you want to do an equation, you look in there and you see what the numbers are, and you put them in your equation, and then it works. But no one knows why those numbers should be what they are, and there's a sense that there ought to be a deeper underlying explanation. Either there is such an explanation, or they're just random chance.
There are a number of constants.
Yeah, so-called constants. They're constant in the sense that they always show up, but no one knows why they show up at the values that they do.
Like the ratios between the various forces.
Exactly, yeah. Why is gravitation so weak? Why is electromagnetism so strong, the strong force even stronger? And these sort of what are called broken symmetries tend to suggest that if you could put the broken shards together into the original mirror, you could see something quite beautiful. And there are many physicists working on the faith that will prove to be the case. So one wants a theory that unifies relativity and quantum mechanics. My candidate would be string theory. But one also wants a theory that at the same time will bring coherence and clarity to quantum mechanics. Just getting the right answer isn't sufficient to the human mind and spirit. There's also a demand for beauty.
Mm-hmm. Well, that's a very subjective aspect. I think you quote one. I believe it's Gertrude Stein you quote, as a matter of fact, referring to works of modern art where they seem weird at first, and when you look at them after a while, not only do they not seem weird, you can't even remember what it was about them that ever seemed weird.
Yes, Ms. Stein, a much underrated writer, said of modern art that you look at it and it looks strange, and you look at it and it looks stranger still, and you look at it and it looks stranger still, and then suddenly it doesn't look strange at all. And there is something like that in science, that a good finding in science ought to be shocking and disturbing. After all, if the job of science were simply to confirm that everything was the way you thought it was in the first place, it wouldn't be much of a job worth doing. The taxpayers and the private donors and everyone have spent all this money, as you referred to earlier, in the support of scientific research. Sent out space probes, launched astronomical satellites, built big telescopes on Earth, particle accelerators, all of this, thousands of people devoting their careers to this. And the society, in return for this investment, deserves some return, and they're getting it. This money was not spent in vain. It's not just a big question mark. There has been phenomenal progress in understanding, for instance, just how the solar system is put together and what its history has been, much less the wider universe. This information is regrettably slow to percolate through to our schools, which continue to keep us all generations behind where we might be in our thinking. But nevertheless, it's there, and it is, in my opinion, central to our cultural heritage. And it says about us that there is such a thing as progress. We have a terrible sort of inferiority complex as a species. We're always going around telling ourselves how terrible we are and that we don't get anywhere and everything's just the same. But it's not just the same, not in science.
Well, it's always puzzled me, I must say, until reading your book, why we spend so much money in the field of astronomy as compared, say, to the social sciences or to psychology, areas that are dear to my heart. I think their funding is much, much less, minuscule compared to what is spent in astronomy. And now, and I've always wondered, well, who cares what's going on in Jupiter or in Alpha Centauri? But it seems to me that the value of this science is that knowledge is really of one piece. That when we think of atoms and molecules, or the cells in my own body are really formed by events that took place in supernovas, and so that we can't understand the tips of our noses unless we really understand what's going on in the distant ranges of the universe.
Well, I think that's right. There are a couple of reasons, Jeff, why the fundamental sciences get more support. One of them is that science is still fairly rudimentary. It is only capable of understanding very simple systems. A star, glorious as it is a fairly simple system. It's the physics equations of what causes the stars to shine are pretty well understood. A human is a much more complicated affair, and science may someday be able to approach humans with the kind of confidence that it just currently does atoms and stars, but we're not at that time yet. So it's just the sheer complexity of human affairs that's so daunting, makes it very difficult to make predictions. And the other is historically, as you say, that we did come from a process that is cosmological in scope. The Milky Way galaxy is this vast system which has, for instance, cycled the atoms in our bodies through, on the average, 2 stars before they got to form us. As you say, some of them supernovae. All the atoms of gold in this wedding ring were produced in exploding stars. So that you want to understand the basics before you try to understand the rest. We got into a lot of trouble, taking the other approach. Historically, we spent an awful lot of time trying to find big, grandiose, top-down philosophies that would explain everything about human affairs by deducing them from a few principles. That didn't work very well. What worked well was to ask very simple questions, like how does a star shine, and try to build up from there. That's science, and it's only about 300 years old.
Mm-hmm. Well, yet it seems there's something frustrating still talking about the universe the way we have been. Nagging at me at the back of my mind are deep philosophical questions, and I know we're going to explore those further in part 2 of our 2-part interview, but let's, in the couple of minutes we have left, if you could begin to take a stab at the very notion of how could something like the whole universe emerge out of nothing?
Yeah, why is there something rather than nothing? One rather simplistic but intriguing answer is that if something hadn't, we wouldn't be here to discuss it. If the universe had not made possible the existence of sentient beings, then the question wouldn't have arisen. But it is a great mystery why there should be such a thing as self-awareness. Have we simply been set down here through some sort of accident, or by God's design as set in some Garden of Eden? Or do we express some aspect of the universe that we ourselves don't understand? And when we inquire about our self-awareness, are we inquiring about ourselves, or are we inquiring about something that takes place on the level of galaxies? When you look at these mountaintop observatories, they look like sense organs. They're sensory organs for the planet. And is that just something we're doing, we humans, or are we participating in some wider process that we don't yet know about because we don't know enough about what life and intelligence means on the cosmological scale?
Well, you're raising the question that consciousness itself may be a property embedded in the universe as a whole.
Yes, and life itself, awareness itself, might be embedded in the universe as a whole. There's some interesting theorizing going on this point.
I'm going to have to interrupt you at this point now, Timothy, because we are out of time.
Right at the interesting theorizing part of that.
We are, but I want to remind you and, of course, our viewers that to check their program guides for part 2 of our 2-part series, because we're just beginning to open up some of the most interesting questions. Thanks so much for being with me.
My pleasure.
And thank you for being with us. New Thinking Aloud is presented by the California Institute for Human Science, a fully accredited university offering distant learning graduate degrees that focus on mind, body, and spirit. The topics that we cover here. We are particularly excited to announce new degrees emphasizing parapsychology and the paranormal. Visit their website at CIHS.edu. You can now download all 9 copies of the New Thinking Aloud magazine for free, or order beautiful printed copies. Go to newthinkingaloud.org.
Book 4 in the New Thinking Aloud dialogue series is Charles T. Tart, 70 Years of Exploring Consciousness and Parapsychology, now available on Amazon.
For early access to our videos and live stream events, sign up for our free weekly newsletter at newthinkingaloud.org.